So, we know that all local extremas have to be critical points, because you can't have a max or min without there being a horizontal tangent line or a vertical tangent line. However, as we just pointed out with those two situations, just because they're the critical point doesn't mean that they are local extrema. So, local extrema are critical points, but critical points are not necessarily local extrema. Alright, so that begs the question, how do we find out if a critical point is a local extrema? So besides looking at the graph, because that's obvious and we're not always going to have the graph, so what do we need to do to determine whether a critical point is a max or min? Well, it all has to do with everything we've been talking about so far, slope. Because slope tells us so much, rate of change. Who would have thought when we were talking about that way back, and not we, you and your other math teachers, way back with rise over run in Algebra 1, that slope would have such a big impact on math? Well, guess what? It does. So, let's see how we can use these things. So, we know that there's going to be a local max and a local min at the turning points. And if we look at this graph, we can see that right here, there's going to be a local max, and we can see at this point down here, there's going to be a local minimum. Alright, so let's look at this graph a little bit more. And let's look at what's happening around that local maximum point. Like, what's the graph doing to create a maximum? Or what's the graph doing to create a peak? Well, if we look here, we can see that as we approach the peak, our function has an increasing slope. And then when we go away from the peak, our function has a decreasing slope. So therefore, we can say that we know the local max exists when the graph changes from increasing to decreasing, which makes sense. Hopefully you had already learned that at some point in your pre-calculus career. Alright, so now let's look at the graph and determine what makes this a local min. Well, we can see that as we approach the local min, we have a decreasing slope, and then when we go past the local min, we have an increasing slope. So similarly, we can say that we have a local minimum when the graph changes from a decreasing slope to an increasing slope. And again, that's all great and all. Those are perfectly fine definitions. However, we're now in calculus. And we're not really concerned with increasing or decreasing. We're concerned with a different aspect of increasing or decreasing. Because when a function's increasing, that means its slope is positive. And when a function is decreasing, that means its slope is negative. So to put this in some more calculus-friendly terms, or using some of our new calculus lingo, we can say that we know a local max exists when the derivative changes from being positive to negative. And then we can do a similar thing with our local minimum. Decreasing is a negative slope, increasing is a positive slope. So we can say we know we have a local minimum when the derivative changes from being negative to positive. Now, fortunately for us, mathematicians were pretty smart, and they put together what they call the first derivative test to help us determine all of these items. So let's talk about the first derivative test. And yes, it's called the first derivative test because 1, we take the first derivative, and 2, there's multiple derivative tests, which we will get through. So what does the first derivative test say? Well, the first thing it says is if a derivative changes from being positive to negative, then the function has a local maximum at that point. So for example, if we would have our critical point, x equals c, and if our derivative changes from being positive to negative, that means c is a local maximum. Then, part 2 says if the derivative changes from being negative to positive, then the function has a local minimum at that particular point. So if we look again at the critical number, if the derivative changes from being negative to positive, that means that critical number, or that critical point, is a local minimum. And then finally, the third condition is to make up for those funky graphs that we had talked about earlier that disproved some of the things we were talking about. If the derivative doesn't change signs, then there are no local extrema. So for example, if we have that horizontal ledge, it goes from increasing to then increasing, or decreasing to decreasing. And same with that vertical asymptote. So if we have our critical points, and it goes from positive, it doesn't have to be it doesn't have to be positive at C, it just has to be positive before and after. And then same thing, it can be negative before and after. That means there are no local extrema at our critical points. So let's take a look at how this works. We want to find the local extrema for the function f of x is equal to 2x cubed plus 3x squared plus 1. So this process of finding the local extrema is really very similar to finding intervals or finding solution sets when we were solving inequalities back in pre-calculus. So our first step is we want to find our critical, if I could spell the word critical, one. Find the, we're going to abbreviate it because I can't spell right now. We're going to find the critical points. And we know to find the critical points, we have to take the first derivative. So f prime of x is going to be 6x squared plus 6x. Now, we know critical points exist when the derivative is equal to 0 or when the derivative is undefined. Unfortunately, fortunately, we have a polynomial, which means the derivative will always be defined, so we just have to check the 0 case. And then we just need to solve for x here, and we can factor out the greatest common factor, which is 6, to leave us x plus 1 on the inside. Based on the zero product property, we can set each factor equal to 0, and then solve for x. And then here, we get our critical points. So, the only place on our graph that can have a local extrema is going to be 0 and 1. We just need to determine whether or not local extrema will exist at one or both of those points, and then which one exists where. So in step 2, we want to apply the first derivative test. All right, so then to do that, we will draw our domain. And the domain of our function, it's a polynomial, goes from negative infinity to positive infinity. And we'll plot our critical numbers, what happened to the infinity there. Let's make that look a little bit better. There we go. All right, we'll plot our critical numbers of negative 1 and 0. Now, we just need to pick test values in each of the intervals, plug those test values into the derivative to determine whether or not it's positive or negative, to determine whether or not the function is increasing or decreasing. So I'll choose x equals negative 2, I'll choose x equals negative 1/2, and I'll choose x equals 1. And again, I'm plugging these values into the derivative, because that's what the first derivative checks. So f prime of negative 2 is going to equal 12. All right, then when I plug in x equals negative 1/2 into the derivative, we'll get f prime of negative 1/2, which is going to give me negative 3/2. And then when we plug in x equals 1 into the derivative, we're going to end up with 12. All right, so looking at these three test values, and I just realized I wrote x instead of 1 here. So let's just make that adjustment. Now let's see, for our first interval here, we can see that the derivative is positive, which means we will be increasing on the interval negative infinity to negative 1. When I plugged in negative 1/2, I got a negative derivative, so that means that we are decreasing between negative 1 and 0. And then when we plugged 1 into the derivative, we got positive 12, which means that we are increasing between 0 and infinity. All right, so then we just have to determine whether or not x equals -1 and x equals 0 is a local max and local min, or neither. Let's see, since we changed from being positive to negative, that means there is a local maximum at x equals -1. And then at x equals 0, we change from negative to positive, so that would mean that there is a local minimum at x equals 0. And there you go. In this particular example, both of our critical numbers ended up being local extrema, with one of them being a local max and the other one being a local minimum. Alright, so then let's just go through a quick review of everything we just covered with local or relative extrema. Again, we said that local extrema exist at turning points and corners or cusps. Local extrema also exist when the derivative is equal to 0 or when the derivative is undefined. That's when we have horizontal tangent lines and vertical tangent lines. However, as we discussed, just because the derivative of a function is 0 or undefined, that does not mean that there will be an extrema. It just means that there can be. And since there can be an extrema, that's why we need to check to determine whether or not a local extrema does exist at a critical point, and we would do that using the first derivative test.